this, most of you would have lost 0.5 marks. So you would be expecting something like 35, but you would have gotten 34.5 because we have asked one question in subjective where we asked you to give us the function which is inverse function, right? Like we have given you a transformation, inverse transformation we asked, right? Almost all. So all the students who have attempted quiz, they gave us in the matrix form, okay, which is not wrong, which is okay. But matrix is just the representation of the inverse transformation. We asked you in a function form. So just the form difference. So that is why we have reduced. So G represents a function there, right? G cannot be equal to a matrix, should not be equal to a matrix. So whatever matrix you have given us, it is matrix representation of G. It's not G. So what we thought is for that we have reduced 0.5 marks, and this 0.5 was reduced for almost all. So almost all the students who have attempted quiz 1 lost this. So with this, what we wanted to convey is we don't wanted to uh, reduce too much marks. Also, we didn't wanted to offer you the full marks because you should be slightly careful when in which form we are asking you the transformation. Okay, whether we are asking you as a function or whether we are asking you to represent the linear transformation as a matrix. So you should be a bit careful. That's it. Both are at the end of the day, both representations are valid. But what we asked and what you gave was two different representations. That's it. Okay,
So
so
are the marks scaled in on
200.
a scale of 100?
Yes,
Okay.
yes, it will be scaled to 100. Yeah, so those will be your final marks. Okay, that is one observation we did, and yeah, there are quite a bit other observations also. As I said, the basic linear transformation which we have given, something like t of 1 is something, t of 1 2 is something else. We asked you to compute t of 10, t of 01. So even in that also, most of the people, like out of 30 odd, most of the people, like at least 50% of the people got it wrong, completely wrong. Yeah, so look at the response sheets. So we mostly whatever copies I corrected, I have given them the reason why it is wrong on the paper itself. But if you others, if you have received your copies without the feedback, you can get the feedback from us in these sessions also. Okay, or mail us or get back to support stating so and so question. I expected some more marks, or so and so question. It was given wrong. Why it is wrong? Okay. By the way, the topper is Muthu Krishnan. He got 39.5. I think he won't mind if I took his name here. That is why I have taken his name. So yeah, if you have any doubts, if Muthu is your friend, do contact Muthu. He will explain you why your answer is wrong. Okay. Okay, so that's about quiz. Let's come to week 6. Yes, Gayatri. You can ask your queries now.
In one activity question, we are getting a cube root. How to solve that kind of thing?
Okay, can you specify the question number to me?
In 6.10, question number 4.
Just a second. Let me open that. me a minute. Okay. Thank God I'm lucky today. So my screen is visible, right? Just 6
Yes, sir.
activity question. Yeah. So no doubts in till 6.9, is it?
No.
Are the answers correct? Everything?
Most of it is correct. Just one small, there was one small.
Okay. So which question? Question number?
4. So 6.104. Yeah.
Okay. So here I think you would have solved it by taking a minus lambda I det is equals to 0, and then you started solving it, right?
Yeah.
If I'm not wrong. Correct,
Yeah.
right?
Yeah.
So that's where you reach cube.
Right.
Cubes and all. So what you can do is observe this. That is what you are going to learn in 6.11 actually. So we have given this question above just to make you think. Even in the lecture also professor would have stated this.
Yeah. Yeah.
When you have seen these kind of matrices where each row sum is the same. So if each row sum is the same,
Okay. Okay.
you see that, right? The sum of the row 1 is -1 plus 2, which is 1. The sum of row 2 is also 2 plus 0 minus 1, which is 1. Oh, sorry, the last row is 0.
Yeah.
Oh, no.
But some relationship is there, I think.
Okay, then there is no shortcuts. I think we should go with a minus lambda I to be 0. And then we will use some trial and error methods.
Yeah.
Okay. So it is 1 minus lambda whole square lambda. Don't be like this. So 1 minus lambda square lambda minus 2 times 2 minus 2 lambda minus 1. But I don't think I made a mistake. Okay. So lambda minus lambda cube minus 2 plus 4 lambda is 0. So lambda cube, am I correct? Is this the
Yeah. Yeah.
lambda cube plus 3 lambda minus 2 is 0. Now you use trial and error method. Starting from 0, you start from 0 and you then move to plus or minus 1, then move to plus or minus 2, then plus or minus 3, and so on. So you check for the integers. Mostly this is called trial and error method. This will hit our first root. This will give our first root. Okay. So if I do this, 0 will not be a root. Even 1 will not be a root. 1 plus 3 minus 2, which is 2, will not be a root. Minus 1 will not be a root. Plus 2, when you reach plus 2, what happens? 2 cube is 8 plus 6 times 2. Oh, this is also not being the root.
No, it's 5 lambda, I think.
Which one is 5 lambda? Yeah, sorry, 5 lambda. Correct. I made a mistake.
Minus lambda cube plus 5 lambda.
Lambda cube minus 5 lambda plus 2.
No. Minus lambda cube plus 5 lambda.
I just multiplied it to minus 1.
Oh, right. Okay.
That will be the same. Now if you start doing this trial and error method, we will be lucky at lambda is equals to 2.
Okay.
Right, when lambda is 2, you will get 2 cube minus 5 times 2 plus 2, which is 8 minus 10 plus 2, which is 0. So lambda is equals to 2. 2 will satisfy this equation. So therefore, one value of lambda is 2. One value of lambda is 2, which is also implies that when you treat this as a polynomial, lambda is equals to 2 is nothing but the root of this polynomial. If that is root, then lambda minus 2 is a factor of this polynomial.
Yeah.
Correct. Right. Then you factorize it.
Okay.
Okay. Then you will get a quadratic equation.
Okay.
Correct. Then from the you know how to solve a quadratic equation, right? From
Right.
there you get the other two roots, and then you can conclude about the algebraic multiplicity and geometric multiplicity. So,
Okay.
right? Eigenvalues, then correspondingly you should compute eigenvectors and look at the dimensions of eigenvectors. That will tell you the geometric multiplicity. And algebraic multiplicity is nothing but the number of times each eigenvalue is being repeated.
Okay.
Okay.
Yeah.
Okay. Hopefully, then 6.10 is also almost correct. So all the answers are correct.
Yeah. And I haven't done 6.11.
Sir, excuse me, sir.
Yes, yes.
You were about to share some shortcut while discussing this when the row sum is same for all the rows.
We will come there. I will tell you. I will
Okay.
tell you. Okay. So maybe I will discuss that. Maybe I will discuss that first. So we will start with that because the other concepts that you have already studied in R2 space. Okay, just generalized version of the concept that you have learned in week 3 and 4. But the shortcut which I am going to say is almost connects to this circulant matrices or the circular convolution. Okay, what does this thing do is I will take a new page. Okay, so for example, we have been given you this kind of matrix. Okay, I will take the same thing -1 0 2 1 1 0 1 0 0, and there is a 1 1 1 2 -1. So you see, this is a matrix. This is, let's say this is a matrix. Now just stare at each row and compute the sum. So if you compute the first row sum, you will get 2 minus 1 plus 0 plus 2, which is 1. If you take the sum of the second row, this will be 1 plus 0 plus 0, which is also 1. So now consider this matrix. Now the last row, if you consider the sum, 1 plus 2 plus 2 minus 2, which is again 1. So if at all you see any matrix of this form where each row sum is being 1, then what happens is, then 1 1 1 will be an eigenvector. Eigenvector with eigenvalue equals to the row sum. So why does it work? I will just show you with this example itself why it is working. Then you'll get the intuition why it will work. So what are eigenvectors? When it is multiplied to the right side to the matrix A, it should just give the same vector but the scaled version of the vector. So some scalar lambda multiplied by the same vector. Right now, if you take this row sums being the same, I take that matrix -1 0 2 1 0 0 and 1, 2, minus 2. And if I try to multiply 1, 1, 1, what am I doing by multiplying 1, 1, 1? If I multiply 1, 1, 1, this 1, 1, 1 goes multiplies with the first row. What happens? The resultant will be just the row sum, right? The first row sum, if you multiply 1, 1, 1, the resulting vector will be the first end. There will, it's a 3 cross 1 matrix. Of course, 3 cross 3 multiplied by 3 cross 1, you will get a 3 cross 1. But whatever you get, they all are just the row sums. Right? This is the first row sum. The second entry will be the second row sum. The third entry will be the third row sum. So if all the 3 row sums are same, you can take that as a common. Right? First row sum, second row sum, third row sum. If I say that is just the row sum alpha, you just say that is equal to alpha. You can pull out that alpha out, or lambda, whatever. So you can pull out that lambda out, then you will be remained with 1, 1, 1. So you are multiplying for this matrix, you are multiplying 1, 1, 1. If you multiply 1, 1, 1, you will get a column matrix which is just the scaled version of 1, 1, 1. That scaling also is nothing but the row sum. Okay. The condition is every row should have the same sum. Only then you can pull out the common term. Even here also, you can see you will get, when multiplied by 1, 1, 1, you will get 1, 1, 1 only. Right? Because you can see this is just the matrix multiplication. You multiply the row, since the row sums are 1, you will simply get 1, 1, 1. This can be written as 1 times 1. So from here you can imply that one eigen value is 1 with corresponding eigenvector will be 1, 1. This will work for any matrix whose row sums are same. You can take any complex matrix. Complex, I mean not the actual complex. Complex, I mean not simple. Okay, you take any big 10, 8 cross 8, or you take anything like that. So you have 2, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. Okay, so you have this, then 0, 0, 4, 0, 0, 0, 0, 0, and then 0, 1, 0, 1, 0, 1, 0, 1. So where your row sum being equals to 4. Okay, 1, 1, 0, 0, 0, 0, 1, 1, and then minus 1, 0, 0, 0, 6, so 0. I'm done with 1, 2, 3, 4, 5. Now I will take 0, 0, I minus I, 4, 0, 1 minus 1. So you can also do this. So 2I, 0 minus I, 1 minus I, 1, 1, 1. Something like this. 1, 2, 3, 4, 5, 6, 7 are done. Okay, let's remove this. Sorry, I can't. Okay, I'll write one more. 0, 0, 1.
So if you are sharing something, your screens appears to be frozen.
Is that so?
Yeah, means it's
No, sir.
just a notepad with.
Yeah, I'm
Okay, it
writing the
might be
matrix.
just.
I'm writing the matrix.
Yeah, but 8 cross 8
No, we are able to
matrix.
see.
Maybe you are. Can you
Yeah,
refresh?
it might be
Can
on
you
my
refresh?
side.
Yeah.
Then
Refresh.
I'll try to reset.
Yeah. So now you see this looks like a very big complex matrix. But whatever trick, or this is not trick actually. This is very evident. So if your row sums are being the same, then if you multiply this one big vector 8, what you will get is just 4 times 1, 1, 1, 1, 1, 1, 1, 1. Okay. So for this matrix A, lambda is equals to 4 is an eigen value. Its corresponding eigenvector is just 1, 1, 1, 8 times. Okay, so this is 8 cross 1. So were you able to get this? So nothing, it is not complex, it looks very trivial, but you just have to be, you just need some practice on these things, that's it. So what is the connection between this and circulant matrices are is, so you see this matrix, the first question. So circulant matrices are generator like this. So whatever the first row entries you have, it will just, you just circular it, you just bring this 2 to the front. This is this circular motion. So you connect 3 1 2 circularly. So 3 1 2 is your first row. Then comes you bring your 2 to the front, that will make you the row 2. Then bring the last entry to the first, that will make you the row 3. So these kind of matrices are called circulant matrices, and circulant matrices special property is their row sums will be the same, because we are using the same numbers, you are putting them in a circular motion, like you bring the last thing to the front and push everything to one step to the right, you bring the last one and keep it at the front, that will give you the second row. Now from the second row you take out the last one and bring that to the front, that will make you the third row. So if you see, if you compute the row sums will be same. So for this kind of matrices, you can straight away say one eigenvalue. So here one eigenvalue you can say is the row sum will be the eigenvalue. So if you compute the row sum here, you will get something like 3 plus 1 plus 2. Right? You don't need to compute, you don't need to do that 3 minus lambda, a minus lambda I and its corresponding det equating to 0 and solve that particular resulting equation and then get the lambda values. You don't need to solve for those things. Okay. So once you have one eigenvalue, which is 6, okay, and you know the properties of, you can use the properties of the eigenvalues, like trace should be the sum of the eigenvalues, determinant should be the product of the eigenvalues. So using these two, you can find the other two eigenvalues. So let us solve this. So you can also solve this, no background needed. So whatever background I explained, that is all needed. We'll using the circulant matrix property, or the property which I have discussed right now. The row sums, if the row sums are same, then the row sum will be an eigenvector, eigenvalue, and its corresponding eigenvector will be 1 1 1. So you multiply 1 1 1 to this matrix, you will see that it will be, the resultant will be 6 times 1 1 1. From there you can check 6 is an eigenvalue. So once 6 is an eigenvalue, what you have is trace of A should be equals to sum of the eigenvalues, right? Let's say lambda 1, lambda 2, lambda 3 are 3 eigenvalues. Then det A should be product of the eigenvalue. You can compute the determinant of this, you can compute the trace of this is 9, 3 plus 3 plus 3, 9. And 1 lambda 1 is the first eigenvalue that we have found is 6. So from here you can write lambda 2 plus lambda 3 is 3. Right? You have one equation here, and even this is also 6. And solve for the det. If I compute the det of A, it will be 27 minus 6 is 21 minus 5 plus 2. Yes. So 23 minus 5, which is 18. So you'll get 18 as det A. You compute this. I may also be wrong. Correct me if I'm wrong. So if det A is 18, that should be equated to 6 times lambda 2 times lambda 3. From here, lambda 2 times lambda 3 will be 3. Right? So lambda 2 times lambda 3 is 3. Lambda 2 plus lambda 3 is 3. So from this, write 1 lambda 2 as 3 minus lambda 3 and bring that and substitute here. You will get a quadratic equation. Solve the quadratic equation. You will get the other two roots also, like other two eigenvalues also. Okay, easy. At least looks easy, right? Is this okay? Am I audible?
Yes. Yes.
Okay. I thought I lost connection.
So just one clarification, or maybe, I mean, I'm not sure if I'm right or wrong
Hmm.
here, but
Hmm.
if while trying to find out the eigenvalues, should we first reduce the matrix to reducible form, or should we directly apply t minus lambda I? That,
No. You cannot reduce it, right?
I mean, this matrix is given, right? Question 1, 3, 1, 2, 2, 3,
Ah, ha,
1,
ha.
and 1, 1.
Ah, ha.
Then should we reduce it first, like
No. If you
row
reduce
reduce?
your matrix will change, right?
Yeah.
Ah, ha.
Then even the eigenvalues will change. You
Correct.
say.
It will change. You should not reduce this.
Okay.
Okay. So if you are
Yeah.
computing it, huh?
I have follow-up question on this because
Yes.
what Gaurav is saying, I sometimes suppose a matrix is given, I am transforming the matrix on the row,
Hmm.
then I am doing some eigenvalue calculation. So it is going to be different compared to the original matrix.
If you perform any row operations, then it will change.
It will change. Okay.
Yes.
Yeah.
Yes, right. You can check that, right? So you take 2, 2, 1, 1. Okay, maybe 0. The eigenvalues for this matrix will be 2, 2, right?
Yeah.
Yeah.
If you try to reduce this, reducing means you just multiply, do some row operations. You just multiply 2 times 0. And
So 0 to.
okay, here it is not changing.
No, let us add on the other side. I mean, okay, that's it.
That will not be the thing. Let me just think about this.
In that we can change R1 in that case. Just multiply 8 the R2 in that and check it. The
You
same
can
matrix.
multiply. You can multiply. Sorry.
No, I am saying just change the R1 itself only, not completely. R1 you can add the R2 in that and it will change, correct? So 2 plus 1 3 and it
Okay.
will.
If I transform this matrix as R1 to R1 minus 2 times R2,
Yeah.
what will I get? 0 minus 2, 1, 2. So this will have different eigenvalues.
But this is not a reduced matrix or reduced form, right?
You take 1, 2, 2, 0. Sorry. 1, 2, 2, 0. So what will be the eigenvalues? 1 minus lambda into minus lambda.
Lambda equal to 0 and lambda equal to 1. Yeah.
No, lambda will not be 0.
Yeah, it is 4. Yeah.
Minus lambda plus lambda square minus 4 is 0. You get lambda square minus lambda minus 4 is equal to 0. So from here lambda will be 1 plus or minus root 1 minus 16 minus 15. So I root 15 divided by 2. Whereas if I just do some row operations, 1, 2, 0 minus 2, right? This is the reduced form. So you do row 2 as row 2 minus 2 times row 1. So for this it will be 1 minus lambda into minus 2 plus minus.
Won't it be minus 4 in the second row? 0 minus 4.
Which one? No,
Reduced
it won't
form
be
1,
minus
2,
4, right? You do R2 minus 2. Okay, 2R1,
2,
right? Yes.
right?
Yeah. minus 4 minus lambda. So minus 4 plus 4 lambda.
Sir, the roots are straightforward. Lambda equals 1 and lambda equals minus 4.
Correct. So lambda will be 1 and lambda is minus 4. Different,
Yeah,
right?
it's a lower triangular matrix.
So if you perform any row operations, you can simply see that if you perform the row operations, your trace will change. If your trace changes, then the sum of your eigenvalues will also change. The sum is changing. So one of the eigenvalues or some of the eigenvalues will change. Okay.
Yeah.
So yeah. So what this lecture is completely on the circulant matrices. Okay. So even if it is if they are circulant, not only these things, so you don't need to do these things. Okay. So there are more than what you see here. So you as of now you can directly see that the row sum is the eigenvalue and one eigenvector is 1 1 1. But if you compute the other eigenvectors also, you will see a strange sort of so what I mean is the other two also you don't need to do all these things. So they are also straightforwardly written. Let's discuss about that. That is so you see this matrix, it looks very big, but you can actually compute all the eigenvalues, eigenvectors very easily. So let's look into that. Okay. 1 second. Yeah. So let's say you have a circulant matrix. So the discussion is on circulant matrices. So as I said, circulant matrices will have an separate form. So that matrix is generated in certain form. Only those kind of matrices are called circulant matrices. So for example, this is a circulant matrix. Okay, so this is the circulant matrix because you can see you take the Roman, it is 1 2 3 4. Now bring the last entry to the first entry, like 4, bring the 4 to the front, and that will make you the second row. That will give you the second row. Right? Bring 4 to front. Next 3 to front. Next 2 to front. That will give you the fourth row. Okay, so these kind of matrices are called circulant matrices. These are not only circulant with respect to rows, they are also circulant with respect to columns. That also you can easily observe. So you have 1 4 3 2. Right? Now bring this 2 to the top. That will make that will create the column 2 2 1 4 3. Then 3 to the top, 3 2 1 4. Then 4 to the top, 4 3 2 1. Okay, in whichever way, you just have to be you just have to bring the last most to the front side. Now these kind of matrices, okay, their row sum will be same. Not only that, if the okay, maybe if the row sum is same, then that will be the first eigen value. The row sum is 10 here, and also the eigenvector is even the eigenvector is 1 1 1 1 with corresponding eigenvalue. The other eigenvalues also are easily generated again using this circulants and powers. So what we do is we just need to go back to math 1 bit. So you remember this cube root of unity, right? e power I pi by n, nth root of unity. So you have to recall that. So here we define some w which is equals to e power I pi by n, and here is 4 now. Okay, so the matrix is 4 cross 4. So and here is 4. So we define w to be e power I pi by 4, which is, if you compute, it will be 1 by root 2 plus 1 by root 2 I. Now w is this. Now what you do is you equate this w as, so we will call w4. Okay. Now you know the fourth root of unities, correct? So w4 to the power 0 is just 0, sorry 1, correct? And w4 to the power 1 is this. Similarly, you can compute w square, w cube, and all, correct? But w power 4 is 1. Correct? Yeah, w power 4 will be 1. Am I correct? I'm
I
not
think
sure
it's
that.
e power I 2 pi by 4.
Right. 2 pi by 4. But that is what I'm thinking. Fourth root of unity will have 1 I minus 1, right? Okay, let me restart this again. So one eigenvalue will be this with corresponding one eigenvector will be this with corresponding eigenvalue as the row sum. The other eigenvalues are you can get it from this nth root of unity. Here it is fourth root of unity. So as we all know, let's say fourth root of unity are the roots of this equation. Alpha power 4 is equals to 1. So if you solve for the 4 roots, you will get the 4 values. So 1 alpha 1 will be 1. Alpha 2 you will get as I, alpha 3 as minus 1, alpha 4 as minus I. Right? The four roots of unity are these 4. And these 4 also can be written as this can be written as e I 2 pi by 4, which is e pi by 2. Okay. So we should start from minus 0. Sorry.
I.
It will be I. We should start from I. It is e I 2 pi by 4. This will give us I. If I just square this, it will give us minus 1. Right? Yeah, this should be minus 1. Then if I alpha cube, I will get minus I. And then finally 1. So these are the 4 roots of unity. I minus 1, minus I 1. Now what we do is for each of them, we define our eigenvectors. So the other eigenvector V2 will be of the form 1 alpha, alpha square, alpha cube. Okay, so this will be one eigenvector corresponding to the eigenvalue, and its corresponding eigenvalue will be, so it's like you are multiplying 1 alpha, alpha square, alpha cube to this A. So what will you get if you multiply 1 alpha, alpha square, alpha cube to this A? You will get 1 times 1, 1 times 1 plus 2 times alpha plus 3 times alpha square plus 4 times alpha cube. Right? Now, if that will be your first entry. So from that first entry, you have to take all this common because the first entry should be 1. What I'm saying is, if you multiply this eigenvector to this matrix, I'll just erase this for a second. So if I multiply that eigenvector, which I just defined, 1 alpha alpha square alpha cube, I should get something like some lambda 2 times the same 1 alpha alpha square alpha cube, right? So what should be this lambda 2 is, if I just look at the first entry, first row, and this column is getting multiplied, I will get 1 times 1 plus 2 times alpha plus 3 times alpha square plus 4 times alpha cube. That will be there, but I have to pull all that thing out so that I will get 1 in the column. Right? So all this lambda 2 should be just the row sum of the first row multiplied to the this whatever vector we said as the eigenvector. So this will come and sit inside this. Is this okay? This is understandable. If I claim this as an eigenvector, then a times that eigenvector should give me some constant multiplied by the same vector. If I have to find that what that something is I can just simply look at the first row and it's multiplied with the vector. That will give me this. But I should not have all these things. I should only have one, because my vector's first entry is 1. Vector's first entry is 1. So all the thing that I am going to get should go as an eigenvalue. Okay. And you can see the other things will also work. I will show you that. So if this is eigenvector, I will write it down for you. 1 2 3 4 4 1 2 3 3 4 1 2 2 3 4 1. Now if I multiply 1 alpha alpha square alpha cube, what I will get is, the first row will be 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube. The next row will be 4 plus alpha plus 2 alpha square plus 3 alpha cube. The next one will be 3 plus 4 alpha plus alpha square plus 2 alpha cube. Next one will be 2 plus 3 alpha plus 4 alpha square plus alpha cube. Now what I will pull out is, I will pull out 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube common. So if I pull that out, if I am pulling that out, I should have the same factors in all the other 3 entries also, right? Only then I can pull out that 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube out. So for that, what I will do is, I will just do a slight manipulation. So on the screen, it looks like all 4 are completely different. But what I will do is, I'll just simply multiply alpha cube to this and divide by alpha cube for the second. For the third row, I'll just multiply alpha square and divide it by alpha square. For the last row, I will just multiply alpha divided by alpha. So if I did this, what will I get is, see this, let the denominator stay as it is. Okay, I'm not changing this denominator, but instead I am multiplying this alpha cube throughout this expressions, alpha square throughout these expressions, alpha throughout this expression. So what will I get is, the first entry is unaltered. The second entry will be 4 alpha cube plus okay, 4 alpha cube plus 1 plus 2 alpha power 5 plus 3 alpha power 6 multiplied by 1 by alpha cube. Okay, you see that? And next one will be 3 alpha square plus 4 alpha cube plus alpha power 4. So this should be alpha power, let's keep it alpha power 4 plus 2 alpha power 5, 1 by alpha square. And the last one will be 2 alpha plus 3 alpha square plus 4 alpha cube plus alpha power 4. And this 1 by alpha. Okay. Now you see we have what is our alpha? This is how we defined our alpha. That's fourth root of unity, which is alpha power 4 is 1. Right. So I can simplify this further. So if I simplify this further, what will I get is 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube. And you see this 4 alpha cube plus alpha power 4 is 1 plus 2 times alpha power 5. So alpha power 4 is 1. So 2 alpha power 5 is 2 alpha. So this will be 2 alpha plus again alpha power 4 times alpha square. Alpha power 4 is 1. So it will be simply 3 alpha square. Similarly, you can see this is 3 alpha square, 4 alpha cube, alpha power 4 is 1, and again 2 alpha power 5 is 2 alpha. So we have the same thing, 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube. That will come even in the last entry also, 2 alpha plus 3 alpha square plus 4 alpha cube plus 1, which is nothing but the same thing. Okay, so we have this. We have this by alpha cube, the same thing by alpha square, and the same thing by alpha. Okay. Now if I pull that out, 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube, I will have 1 by alpha cube, 1 by alpha square, 1 by alpha. But still we didn't get this 1 alpha square alpha cube. Again, you just do a little bit of manipulation. That's it. You just multiply alpha and divide it by alpha. What will you get? Alpha, and this is alpha power 4. So you just multiply alpha square and the denominator will become alpha power 4. You just multiply alpha cube, the denominator will become alpha power 4, and all this alpha power 4, alpha power 4, alpha power 4, everything is 1. Finally we get 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube multiplied by 1 alpha square alpha cube. On the left hand side we have this. So on the left hand side we have this. Our matrix is getting multiplied with 1 alpha square alpha cube, and the result is can be written like this. So some scalar multiplied by 1 alpha square alpha cube. Even that scalar is also known to us, so we can compute this. So as we know alpha power 4 is 1, right, from here we can actually write down what is alpha square, what is alpha cube. Right? What is alpha? The first root. Alpha is I. Alpha square will be minus 1. Alpha cube is minus I. Right? So alpha square, alpha cube, alpha power 4. These are the 4 roots of unity. So from there you can write this root also. So this is nothing but 1 plus 2i plus 3 times minus 1 plus 4 times minus I. So you will see that you will get minus 2 minus 2i. So minus 2 minus 2i as the another eigenvalue, and its corresponding eigenvector is this. So 1 alpha square alpha cube, its corresponding eigenvalue is minus 2 minus 2i. Okay, so this is the second eigenvector we get. and this is the second eigenvalue. So the first eigenvalue and first eigenvector will be just the row sum. You do the row sum 1 1 1 1. Okay, so v1 also I will write it here. V1 will be just simply be 1 1 1 1, and its lambda value is 10. Okay, so we got 2. So still 2 are left, right?
So one question here,
Yeah.
I means I followed through all this calculation, I got that, but
Hmm.
how did we means alpha power 4 is equal to 1? Um,
No,
that
if
was
alpha power 4 is 1, then this will be an eigenvector. So circulant matrices will have eigenvectors as something of this form where that alpha is satisfying that condition. It's just the fourth root of unity. So that is what the property of circulant matrix has. If I take 5 cross 5 circulant matrix, okay, then the eigenvectors will be of the form 1 alpha alpha square alpha cube alpha power 4, where that alpha will be satisfying the condition alpha power 5 is equals to 1. So it comes from fifth root of unity. Okay, so
and how
that's
did
the
we get
fact.
to this conclusion? I mean, is there a proof for this, or that's like
I think there is a proof for that. Also, it is evident from here also, right? If alpha power 4 is equals to 1, only then this will be an eigenvector. If alpha power 4 is not 1, then this won't be an eigen vector, right? So maybe proof by contradiction, or you take the claim and try to disprove it. So we took the claim as like this, and it is turning out to be our claim is true.
okay?
Okay, so we claim that this will be an eigenvector, and we cross checked it whether it will be an eigenvector or not. It turns out that it is an eigenvector, because when it gets multiplied to the matrix, it is giving me the scaled version of that vector, which is nothing but the eigen. That's the property of eigenvector, right?
Yeah.
So from there, but even I will check on this. Even I am not sure about the mathematical proof, existence of mathematical proof behind this. So can we prove from the front? So can we prove that given an circulant matrix, can we prove the nth root of unity
But
is
besides the
from?
proof, if I have to state it for a circulant matrix, the
Hmm,
first eigenvector is n ones, means 1 1 1 1 n
correct,
times.
n
The
time.
second one is alpha power n equals 1. So 1 alpha alpha square alpha 3 up to alpha n minus 1.
Alpha n minus 1, correct,
That will be the second eigenvector.
correct.
But for that eigenvector, I'll have to find out the eigenvalue somehow. And this is what we did. Like,
So the eigenvalue will be, see, the first, you see, this first entry will always be 1 for all
yeah.
the next vectors also.
Okay, okay. So it will be like sum of these 1 plus 2 alpha plus 3 alpha square plus 4
Correct.
alpha cube.
So the first
If it
row,
is
when it get multiplies to the vector,
okay,
whatever the sum you get, that will be your eigenvalue.
okay, okay,
Okay. So not only
okay,
this vector, it turns out that the third vector will be just the squares of this 1 alpha square, alpha power 4, alpha power 6 will also be an eigenvector. Again, if you want to cross check, again, claim this, you put it here, you see that somehow you can do these manipulations, and then you will finally see that this will be an eigenvector with its corresponding eigenvalue as, again, you take 1 alpha square alpha power 4, alpha power 4 is 1, alpha power 6 is alpha square again, right? This will be 1, this will be alpha square. Okay, you can check this again. So you take, I'll just take that. So you take this now, this is alpha square. This is 1. So it's when I'm saying alpha square, alpha cube, I mean that alpha is I here. Okay. So it's 1 I minus 1 minus I is one eigen vector. And here it is 1 minus 1, 1 minus 1 is another eigenvector. So you can directly see that 1 minus 1 plus minus 1. If I compute this, I'll get 1 minus 2 plus 3 minus 4 and 4 minus 1 plus 2 minus 3, 3 minus 4 plus 1 minus 2 and 2 minus 3 plus 4 minus 1. If I simplify this, I will get 4 minus 4 minus 2 and 3 minus 1, 2. You get minus 2, 2. Okay. So from here you pull out minus 2 as common. You will see that 1 minus 1, 1 minus 1. So here minus 2 will be the root. Sorry, it will be the eigenvalue and its corresponding eigenvector is this. So lambda 3 will be minus 2. Okay. Or you take it as alpha square itself, and then you will see that 1 plus 2 alpha square plus 3 alpha, sorry, plus 3 plus 4 alpha square will be your eigenvalue. If you compute it, you will get it as minus 2. Okay. So anyway, it will work. And the last vector, by now you should have guessed this.
Cube.
Correct. You just cube it. This will be an eigenvector, and you don't need to compute for the eigenvalue. You have 3 eigenvalues with you. You just look at the trace. Trace should be 4. You just add these 3. You will get 6 minus 2i. So therefore, it should be minus 2 plus 2i. Also, you can also check that if minus 2 minus 2i is a root and it's an real entry matrix, so you will have its complex conjugate also as a eigenvalue. Okay. So whenever you have circulant matrices, the computation of eigenvalues and eigenvectors are very easy. So you don't need to follow the traditional method, a minus lambda I, taking its determinant and equating it to 0. So you don't need to do that. Okay, so you can follow this approach. Okay.
While
So I think
while finding out the fourth vector, you said that we can find it from the trace. Well, trace should be equal to trace means
should be equal to the sum of the eigenvalues.
Yeah, but we have not yet found the fourth vector. So trace, we should know the trace beforehand, right?
A trace, you can see it from the matrix itself, right? So whatever the matrix given to you, this is given to you, right? This is a circular matrix given to you. Its trace is 4, right? The 1 plus 1 plus 1. So this is the trace.
Okay.
I hope this is known to all, right? Sum of the diagonals is nothing but the trace. Sum is trace.
Thank you.
Yes. Okay. Or you can, if you don't know this also, it doesn't change anything. You just have this vector, go get it multiplied to the matrix, and from there you can get it. Okay.
Yes, sir.
Okay. So yeah. What else? So this is almost 6.11. It's called circular convolution. If you guys are studying this signals and systems, by now you would have seen what is convolution sum is, right? Convolution.
Yes, sir.
So look into the lecture. So what happens is you have a series of inputs that goes into a filter. with impulse responses H0, H1, H2, H4, and you will get a series of outputs. And inputs and outputs and this impulse response is connected in some fashion, right? It's called convolution sum. You can write down the output as some input times the convolution values, the constant values, right? So that's convolution. And if you try to write down the matrix of that convolution, you will see that the output can be written as some matrix multiplied by the input. The whatever the sum matrix which you are going to get, it will be in circulant matrix form. Okay, so this is all about lecture 6.11. So you can go watch it out. So I have briefly explained it. So you can solve these kind of examples also. So this is a circulant matrix. So once this is a circulant matrix, you can straight away see that if you just sum this, you just do the sum. Whatever the sum is,
45.
that will be your one of the eigenvalue. Okay. So C is 45 is an eigenvalue, and D is, you see, 1 1 1 1 1 1 is an eigenvector of A. So that D is also pretty straightforward. But for diagonalizability, and one more thing is circulant matrices are diagonalizable. Okay, straight up.
Sorry, what did you say?
Circulant matrices are diagonalizable.
Okay, so
They will have distinct eigenvalues.
okay.
Okay. Yeah. So I think these are the things that you should know about the circulant matrices. And if we go slightly backwards, I think 6.10 is about just the upper triangularization and powers of diagonalizable matrices. This you would have seen in R2 space, right? So you have a matrix A. If you want to diagonalize it, you have to write down it in the form of some S inverse, some P times or some D times S, where this D is the diagonal matrix and S is made up of the eigenvectors of corresponding eigenvalues. Right, so the same thing follows. So if at all you can write any matrix of that form, then that is diagonalizable, or else it is not diagonalizable. In other words, if you are getting distinct eigenvalues, then that particular matrix A is diagonalizable, or else it is not. So the same thing here also. So you see which of the following matrices are diagonalizable. The only thing you have to do is you compute the eigenvalues. If your four eigenvalues are distinct, then they are diagonalizable. If your four eigenvalues are not distinct, then they are not diagonalizable. Okay. So yeah. What else? Yeah, I think all this algebraic multiplicity, geometric multiplicity. We studied about determinants also here. But I hope most of you know about determinants, right? How do you take the determinant of a matrix here and its corresponding properties? Do I have to go through it again? And the first lectures are just the algebra, matrix algebra. How do you add two matrices? How do you multiply two matrices? When are two matrices are multiplicable? All these things. So from there, so this is 6.1. 6.1 we have seen addition and multiplication of matrices. So if you have two transformations, linear transformations, and if you add those two linear transformations, their corresponding matrices will also get added up. And when you take the composition of two linear transformations, then its corresponding matrices will get multiplied. Right? So that's how it is. From there, you see that matrix sum is, it will just add up entry by entry, and matrix multiplication, I think you should all know this. How do you do matrix multiplication? You take the first row, first column, you multiply each entry to, so 1 1 will get multiplied to A11 will get multiplied to B11, A12 will get multiplied to B21. So first row first entry will get multiplied to the first column first entry. Second row first row second entry, first column second entry, and you take the sum of it and finish the matrix. So you progress. So whenever you are in the ith row jth column, so whenever you are multiplying ith row with the jth column, you should be a little bit careful. So like J1 will get multiplied to 1J. I1 will get multiplied to this happen. So if you are multiplying ith row with the jth column, or the resultant mat corresponding products I comma jth entry, you should take the ith row of the first matrix and jth column of the second matrix, and this will be AI1, AI2, and so on. This will be B1J, B2J, and so on. Okay, you have to take this, multiply it with this, and take this, multiply it with this, and you do the same for the all the other things. And whatever the product values you get, you just add it up. Finally, that will give you the I comma jth entry in the product. So these things are pretty straightforward. I don't want to spend too much time on this, but you should be a little bit careful when are products defined and not defined and all. And these are how do you do multiply two matrices. Okay, so you just have to multiply and see whether they are. So you just have to take the LHS, do the matrix multiplication, just see whether it is being equal to the right side or not. Okay, so it's 6.1. 6.2 is again we talked about addition and multiplication. Here we talk about powers and inverses. So powers, how do you take powers of matrices? How do you find the inverse of any matrix? So all these things will be is taught in lecture 6.2. So even this also straightforward. It has direct formulas nowadays. Nobody wishes to solve it by hand. So you just input this to a system or computer. It will give you the output. So there are many tools that nowadays that performs almost all the linear algebra problems with one shot. So you just have to input. It will give you the output. Okay, but it's good to know about how do you compute all these things. Okay, and 6.3 is very well known with larger matrices. You know how to compute eigenvalues and eigenvectors for 2 cross 2 matrices. But if the matrix is more than 2 cross 2, like if the order is 3 cross 3 or 3 cross 4 or higher dimensions, how do you compute the eigenvalues? Sorry, 3 cross 3 or 4 cross 4, or maybe even higher dimensions, how do you compute the eigenvalues and eigenvectors? So for that, if it is 3 cross 3, we will not go beyond 4 cross 4. If we are giving you a 4 cross 4 matrix, then check for these kind of things. Either it will be a circulant matrix or it will be an upper triangular matrix where the eigenvalues are pretty much visible on your screen or face straight up. Okay. For 3 cross 3, what you do is you just have to guess the first root. You just do the trial and error method. You will get the first root and then you can compute the other two roots. Okay. So here you see this is a matrix and we just asked you if it is a diagonal matrix, then whatever the entries on the diagonal, they will act as the eigenvalues, right? So that is
Here I had a doubt. In lecture, this existence of proof, 6.4.
okay.
Existence of eigenvalues, proof 1 and proof 2. So proof 2 is based on determinants.
Determinants, correct. So
Yeah.
we have used
Proof 1, how do we get the eigenvalues using proof 1?
okay. So let me recall what this proof one is. So can you give me an idea?
It's
Idea
mostly
what-
on singularity. Like if it is singular, then it's
Okay. I got it. So yeah. So it's about considering some n plus 1 vectors.
Yeah.
So you consider an operator. Okay, so operator can be from any fn to fn. Okay. So now consider a vector v and consider tv. Okay. And consider t square v. So like this, consider t power nv. Okay, you just do composition of the same operator again and again. So now you have n plus 1 vectors. Correct? So starting from v, you will have n plus 1 vectors in n dimensional space. Correct? In fn. So in fn you have, so this tv, t square v, everything will be in fn only, right? Even v will also be in fn. So you have n plus 1 vectors in n dimensional space. What we know, if we have more vectors than the dimension, then definitely they will be linearly dependent.
Yeah.
Correct? If they are linearly dependent, then what's the condition I know? Its linear combination will be equals to 0 for non-zero coefficients. Correct?
Yeah.
And yeah, you write it down. an tn v and an minus 1 tn minus 1 v and so on. Finally, we have a1 tv plus a0. You cannot write v, you should write iv. Right? All these are operators, and you just take an identity operator. Okay, iv is also nothing but v, but just not to have any irregularities, we take I. Now, what can I do? I can write this as an tn. So I can pull out this v common out. Plus an minus 1, tn minus 1, and so on, a1 t plus a0 I of v. Right? So operations on linear operators. So I can do this. I can write it in this way. Now this, you see, this is an, let's for suppose say instead of t there is some x, some variable x. It's an n degree polynomial in terms of t. Correct? If it is an n degree polynomial, it will have n distinct roots. Right?
Yeah.
And some of the roots may repeat also. That is also possible, right?
Right.
So you may not get all distinct, but it will have at most n roots. But if you include the multiplicities also, it will have n roots. But if you don't include the multiplicities, then the number of roots may be lesser than n also. So the roots may repeat.
Okay.
Now, if you say, let's say x alpha 1 to alpha m are the roots. Okay. Then how can I write this whole thing? If they are the roots, I can write it like some t minus alpha 1 I times, there will be some powers. We don't need those powers, but t minus some alpha 2 I and so on t minus alpha mi. This should be equals to this, and this times v should be equals to 0. Now what does this imply? This implies, so I'm writing this whole thing like this. If at all it has m roots, I can write it like this, and there will be some powers. I don't consider the power. So if it is square also, not t minus alpha 2y whole square, considering that or this, ultimately it doesn't impact much. You can consider this itself. Okay, so you can just consider the distinct roots and write them as the product. Okay, now what does this say? This v is an so if some transformation times v is giving me 0, implies that v belongs to null of the transformation, right?
Yeah.
T minus alpha 1i, t minus alpha 2i, and so on, t minus alpha mi. Okay.
Okay.
Now from here we will just claim that one of the, this is the claim again. So you can prove like this also. What you will claim is one of t minus alpha j I is singular. Okay.
Yeah.
So if why it should be singular is, if it is not singular, what happens is the whole null. So this is not singular, this is not singular, this is not singular. Everything is not singular. Null of a not singular transformation is 0. Right?
Yeah.
Null of t will be 0 if and only if t is invertible or t is not singular.
Right.
Right? So here what we know is v is non-zero. That's our assumption. We took a non-zero vector v. So if it is non-zero, then there should something should exist in this null. If something should exist in this null, then one of the factors should be singular. Only then the whole thing will become singular. Right?
Yeah.
From there you see that from there you see that there exists an alpha j such
Yeah.
that t minus alpha I is singular, and that alpha j will be your eigen value.
Okay.
Okay.
So with using this, how do we solve a problem like?
Nothing. This is just a proof that there will always exist eigen values for any matrix.
Oh, okay, okay. So which
This is
means
just a
that
proof.
we can apply the same determinant for from problem point of view.
Yeah, with respect to the problem point of view, you can use that whatever traditional way we know. So we'll take the det of a minus lambda I equals to 0. It will give you a polynomial in terms of lambda, and solve for that, solve the polynomial and get the roots.
Okay.
Okay.
Yeah.
And this is one proof, one mathematical proof stating that if you have a matrix A, then A minus lambda I will always have a solution.
Yeah.
Okay, so yes, that's the only thing they wanted to convey in this particular lecture.
Okay.
Okay.
Thank you, sir.
Yeah. So yeah, anyway, this is what 6.4 is. So even though if
Sir,
you didn't understand, Yeah.
Sorry
Yes.
to interrupt you.
yes,
If we have a matrix A, then A minus lambda I will always have a solution. Right?
determinant of A minus lambda I will always have a solution. Equals to 0 will always have a solution.
So this is true even if A is singular.
It will be true.
Okay.
So all that we are doing is we are just simply taking A minus lambda I, right? Why we are taking that A minus lambda I? So and we are saying that A minus lambda is singular. So if it is singular, then we say that null of A minus lambda I will contain something, right? This is what we claim, right? We claim all these things.
Yes. Yes.
Uh, though if that means if null has something, rank should not be the full rank. If rank is not full rank, then there should be some linearly dependent rows. So from there we write down the equation for dependency, like linear combinations, and then solve for lambda, right? Why should we do this? Only if we are guaranteed that a minus lambda is singular, only then you can do this, right? Or else you
Yeah.
cannot do. So for guaranteeing that a minus lambda is always singular and there will always exist some lambda which makes a minus lambda as singular is what this proof is.
Got it, sir. Thank you.
And one doubt: if suppose a matrix is 3 by 3 and one of it has a rank 2, so that means determinant will be 0 for that matrix.
Right, that will be 0.
Okay.
That's the property, right? If determinant is being 0, it implies that some of your rows are linear combinations of other rows. Only then that will be 0.
Yeah.
Okay, if that is happening, then rank will not be the full rank. Right? That's a property. That's a good property. I think you would have studied in the school, but anyway, you can use that also.
Okay.
If A is not full rank, then that A is 0. Okay, so you can use this.
Yeah.
Yeah, so that is about 6.4. Okay, so whatever I discussed here, that is what even in the lecture it is the same. It is just the proof, existence of eigenvalues. It is one proof. And even in 6.5, we have shown the other proof using the determinants, whatever we do, the traditional approach. So we compute the det of a minus lambda I and equate it to 0, and then form a polynomial with respect to lambda and solve the polynomial to get the roots. Solve the polynomial, and whatever the roots you get, they will be your eigenvalues. Okay, so that is all about 6.5, and I think you can solve these examples also. And in 6.6, we again talk about the algebraic multiplicity and geometric multiplicities of each eigenvalues and eigenvectors. So once you study about the eigenvalues, eigenvectors, then the next thing you study is their algebraic and geometric multiplicity. So the same definitions holds. So whatever algebraic multiplicity is just the multiplicity of the root or multiplicity of the eigenvalues. How many times the eigenvalue is being repeated is what algebraic multiplicity of that particular eigenvalue. And geometric multiplicity is, so for an eigenvalue, the dimension of the null space of that particular eigenvector, its corresponding eigenvector, will be your geometric multiplicity. So all these things are just the same, which we have learned previously. The same thing with higher dimensions. That's it. Okay, 6.6 is also 6.6 is that. And 6.7 we start talking about the diagonalizability. So when do we say a matrix is diagonalizable, and when do we say the matrix, if at all it is diagonalizable, how to diagonalize them, that you study here. And 6.8 is again change of basis. So this will have big expressions. You just have to be a little bit attentive while you watch the 6.8 lecture. So this will have very strange notations. So there will be tilt into the picture. You should be a little bit careful. That's it. Yes, Satyan.
Sir, could you please explain change of basis once again?
Okay. So change of basis is okay. What it does is it represents our matrix. So you can, okay, I will explain this briefly. Okay. So what you have a linear operator. Okay, let's say it is going from some fn to fn. Right. Now, this linear operator can be represented with respect to a matrix in terms of a matrix, which we call it as MT, M of T. And how does this matrix is defined is, you consider a basis for the input. So usually we will consider canonical basis. So if I consider canonical basis, okay. So what is the canonical basis for Fn space? Or let's stick to R for simplicity. Even this will work for complex also. So what will be the canonical basis? E1, E2, and so on, En. Similarly, a canonical basis for output also. So we will not worry about input output different bases. We will just stick to the same basis that has for input and output. Now, how do I define this matrix is this way, right? It's you take the first vector in your basis and you look into the transformation of that vector, which is T of E1, and whatever the vector you get, that will be your first column of your matrix. Similarly, T of E2, and similarly T of E3, and so on, T of En. So the last basis and its transformation will come and sit in the last column, right? So this is with respect to canonical basis. And you know what? This operator T, this linear operator T, can be represented with respect to this matrix, and this is not unique. The matrix representation may not be unique. So if I change the basis, the matrix representation will change. So what does that mean is, if I take another basis, another, let's say some second basis, let's call this a second basis. Okay, let canonical be the first basis, and if at all it has to be a basis, then they should be linearly independent. The only condition for basis is it should be linearly independent, and I should have n vectors. That's it. So I will have v1, v2, vn as my second basis, where all these vi's are linearly independent. Okay, so Li stands for linearly independent. Now my m of t, I can represent it as, I should represent it as T of v1, T of v2, and so on, T of vn. Okay, and this, okay, so let's say this is m1, m2. So both the representations are for the same linear operator, but with different bases. Okay, so that is why matrix representation of a linear transformation is not unique. So if you change the basis, your matrix representation will change. But without this linear transformation, or if you have these two matrices, can I convert from one basis to another basis? So I have this, and I have this, or I have this and this, and I have to generate m1 of t. So what I am saying is, I have t and m1 of t. Now, can I compute, or can I find m2 of t? Or the other way around. So I have, so this is first thing. I have the linear operator t and m2 of t. So m2 of t, I mean you have the basis and the matrix. Can I compute m1 of t, which is the canonical basis matrix? So can I simply convert one from another? This is the question. So the answer to this is what change of basis is. You can actually convert from one matrix to another matrix. Okay, so you just have to do some manipulations. So if I just go through that, you will still get confused. Professor has explained it neatly, but let me write down the final output, okay, for you. So let's say this is the basis you have. This is the basis you considered, okay, which is not canonical. So canonical to another basis to canonical is widely used, but you can also do from one basis to another basis. That is like an extra step to the canonical basis. Okay, so I think even the expressions are also a bit time taking to write it down, but so you see, this is the idea. So take this idea. Okay, so think about this. You are representing linear operator as with respect to one basis, and its matrix is something different, and with respect to another basis, its corresponding matrix will be something else. But is there a way to change from this canonical basis to another basis, or the second basis to the canonical basis? And there are straightforward formulas to you. If I have to derive it down, I think the 25 minutes will not be sufficient. So I have to stop that in between. But I urge you, just go back to the lecture. Just watch that lecture. So that is the best explanation I have seen so far. Okay. So it's just a formula, straight formula you have to use. That will just use the matrix formed by this V1. See this V1, V2, Vns are vectors. Okay. So if you write down this as V1, V2, and Vn, this will form a matrix. Its matrix and its inverse matrix and this M of t with some combinations will give you back the M1 of t. Okay, so something, it will have something like that. So actually, I kind of unable to recall the exact expression. If I sit down solve for that, I can solve for that, but if I sit and solve for that, we will eventually end up reaching the same expression that we got from the lecture. Okay, so it's good. I suggest you to, it will save your time. Okay, so that is why I'm referring you back to the lecture. You watch the lecture. If you are unable to understand that, come back on Friday. Friday is our session, 7 to 9. Okay, then we will sit and try to solve it. It is a time consuming thing, so that is why I'm not. I don't want to do it now. Okay, is that okay? So, but this is the idea. This is where the idea starts, and slowly you write down this vector as the combination of this canonical basis. Okay, and from there you will form the big matrix, and you just have to invert it, and you have to do many other things there. Okay, look it up, look it into the lecture. If you still have any doubts specific to any lecture point, or maybe I will come up with the slides. So with the professor slides itself, it will be very easy to write. Okay, or do it with 2x2. Understand it with 2x2, then this will be much more easy, a little bit easier. Okay.
Yes.
So yeah, final conclusion is, so the starting point is this, but the ending point you can get it in the better way if you watch the lecture. End result. Okay. Yeah. And next 6.9 is power of diagonalizable matrices. This again we have seen this previous also, in previous case also. If it is diagonalizable, you can write any matrix A as some S inverse ds. Now if I consider A power 5, it will just simply be S inverse D power 5 S. So this S inverse and S won't change. It will be as it is. You can take the power for the diagonal alone. And finally multiply this S inverse and S to it, you will get A power 5. Not only A power 5, you can compute A power M, and that will be simply S inverse D power M S, where this S is the, so this D is the diagonal matrix, diagonal matrix with diagonal entries are eigenvalues. The diagonal matrix with entries as eigen, with the diagonal entries as eigenvalues. Okay, and this S inverse are sorry, S is V1 to Vm, where V1 to Vm are the eigen, Vi's are the eigenvectors. Eigenvectors corresponding to the eigenvalue I. Corresponding to eigenvalue I. So this is the same thing which we learned in 2 cross 2. Even the higher dimensions also the same. So even here you see, you consider this matrix, you see that this will be diagonalizable. Is that so? Yeah, I think it will be diagonalizable. You need one more condition also. I forgot to mention that if at all this is diagonalizable, doesn't look like it is diagonalizable. Can we try this? Can we try this problem? Gayatri, you have solved this, right?
Yeah, you mean the repeated eigenvalues?
Yes.
Actually, the lecture, professor told that even if you have repeated eigenvalues, if
Algebraic multiplicity should be equal to geometric multiplicity.
yeah.
But yeah, if that is the case, okay. Here it is diagonalizable. Sorry. So this is diagonalizable. So one thing is, if you have, I forgot to mention this, if you have distinct eigenvalues, straight away it implies that it is diagonalizable. But if you have some repeated eigenvalues, then whatever the repeated eigenvalue is, then it's algebraic multiplicity and geometric multiplicity should be the same. Okay. So finally, if I have to combine these two, what should I say is, if a matrix is diagonalizable, then that matrix should have, if a matrix of order n cross n is diagonalizable, if it has n independent eigenvectors. Okay, so the second thing is, if you have, even though you have repeated eigenvalues, then if your algebraic multiplicity, if it is being equal to the geometric multiplicity, then what it implies is, for the same eigenvalue you will get different eigenvectors. So if your root is repeated, if your eigenvalue is repeated twice, then its algebraic multiplicity is 2, and if you compute the geometric multiplicity, if it is also 2, then what does it imply? The null space is spanned by 2 independent eigenvectors, right? So even though the root is being repeated twice, you will have, for that particular root, you will have 2 independent eigenvectors. So just like that, if it is repeating n times, then algebraic multiplicity will be n, some m, let's say if it is repeating m times, the algebraic multiplicity is m. If geometric multiplicity is m, then that means it has m distinct eigenvectors corresponding to the same eigenvalue. So even though it is repeated, its corresponding eigenvectors are distinct. So from there you will get the m distinct eigenvectors. For the other eigenvalues, you will get the eigenvectors. So if you combine all those things, you need to have, for an n cross n matrix, you need to have n independent eigenvectors. Okay, so this is one thing you observe in higher dimensional matrices. Okay, so use that. So this is diagonalizable. Diagonalize this, and then you will get something like A is equals to some S inverse some ds, then compute A power n S inverse D power n s, then tend n to infinite. So when you tend to n to infinite, this S inverse and S will say as it is, limit n tends to infinite D power. So whatever you will get after tending n to infinite, you will get a matrix here, then multiply that matrix with, on the right, multiply it with that S inverse, and on the right hand side multiply it with S, you will get A. Sorry, you will get this answer. Okay, and 6.7 is just using a specific basis. You can always convert any matrix to an upper triangular matrix. Okay, so that is dealt here, and 6.11 is just the convolution. Sorry, circle and matrices. Okay, so the main things that you must know is from this linear algebra is these things. So you should know what a linear transformation is. You should know what a linear operator is. Once you have a linear operator, you should know its corresponding, how to compute their corresponding eigenvalues and eigenvectors. And once you have the eigenvalues and eigenvectors, you should know their algebraic multiplicities and geometric multiplicities, of course, and then the diagonalizability of the matrix. Okay, so these things you should definitely know. So if you claim that you know linear algebra, then whatever question that is coming from these concepts, you should be able to answer them. So other things, you are unable to do this. So even change of basis is also quite a bit important. So if you forget the circle and matrices, it's fine. It is one concept. If you forget, what else? The properties of determinants or properties of trace, or those are all acceptable. But if you say that you know linear algebra and you have studied linear algebra, and if you are not able to connect linear transformations with matrices, then you didn't do linear algebra correctly. Okay, so this is the heart of linear algebra. So eigenvalues and eigenvectors, and the diagonalizability of a matrix, and where this matrix is coming from, it is coming from a linear transformation. So this is the heart of linear algebra, and you should definitely learn these skills. Okay, so we were about to come to the closure of the theoretical part of linear algebra. So till week 8, so this is week 6. Week 7 we will study about inner product spaces in R and in Cn dimension or Fn dimension. We'll study inner product spaces, and in week 8 also we extend the inner product spaces and connect this inner product spaces with the linear transformation. Finally, we studied linear transformations, we will study inner product spaces, and in week 8 we will connect these two and study the adjoints. Okay, and that's where we come to the end of theoretical part of linear algebra, like mathematics side of linear algebra. And from week 9 you will see the applications of linear algebra in our electrical engineering, electronics, whatever. We'll see some applications from week 9. Okay, so by week 9, by when we reach week 8, you should all be comfortable with these concepts. So whatever the concept that I just mentioned. Okay, so linear transformation, its corresponding matrix, once you are in the matrix world, then it's eigenvalues, eigenvectors, and then their algebraic multiplicities, geometric multiplicities, and there are certain properties also connected to eigen vectors. If eigenvalues are distinct, then their eigenvectors are linearly independent and all. And we will also study more about this in while we study operators, sorry, adjoints. So when we study adjoints, we will study more on this eigenvalues and eigenvectors and their connections. Okay, so you should be very, very comfortable with these terminologies and all. Only then week 9, week 10, week 11, week 12 will make sense for you. Or else you will be like, what is happening there? Okay. So with that, I think, yeah. No.
Should we send a mail to support to send us the papers, or will they
Ah,
send-
no need, no need, no need. They will send. We are constantly sending them reminders to share the copies with you. But I think there is some issue on the back end. I have to check with them again. So maybe tomorrow morning I will check with them again.
Okay.
Okay. Yeah. Okay. Anything else? Yeah, I think Satyam. So if at all you are unable to understand that change of basis, you will do it on Friday. Okay.
Okay, sir.
Okay.
Thank you, sir. Good night.
Yeah. Thanks all for joining and have a good day.
Yeah.
Bye.
Thank you very much, sir.
Thank you, sir.
Thanks.